count up, so I don't know. It's kind of weird. All right. I count them at the end and make sure that they're all there. Mailbox or they don't have? I think they maybe in my mailbox. Send me an email, I'll check. All right. So we have to talk about something, guys. We have to talk about something. We have to talk about the cell. And we have to talk about the cell and the cell's nucleus. With its inner membrane and its outer membrane that's consistent with ER. We have to contend with the Golgi. And then we have to contend with the fact that, remember, that the rough ER is rough because it's studded with ribosomes. Now this is what would, I mean, you'd have this huge Golgi, this huge ER in a plasma cell when it goes from B cell to plasma cell. You understand, guys? So if you see one of these plasma cells in the blood plasma, everybody hear me? If you see a plasma cell in blood plasma, guys, that's cancer. That B cell got no business being it. B cell, what you doing in that bloodstream? What's the matter with you? You don't belong there. You understand me? B cells don't belong in blood plasma. They don't. They belong in the lymph nodes, in the germinal centers. They belong associated with mucosal layer. They belong associated with the glandular cell that's secreting mucus on the mucosal layer, or in the gut, which is also mucus, because we got to keep. Remember, we're all shit eaters, right? And separately, we got to keep it. We got to keep it greased all the way down. We got to keep it greased. Everybody follow? Because if we don't keep it greased, then what happens? Then we really full of shit. Yeah? You got me? Then we really full of shit. Yeah? Because now you're constipated. That's what happens when you take what? Drugs that inactivate the parasympathetic response to GI, which would stimulate motility. So when you're taking drugs that affect the GI, like hydrocodone, all right, those morphine-like substitutes, that they suppress GI activity. They reduce secretions. Non-steroidal anti-inflammatories can also cause this. Aspirin can also cause this. Everybody hear me? Long-term use of the aspirin can cause it. So you can increase your risk for ulcers. Because why? Because you took too much of this stuff and you prevented the release of mucus in the lining. In that mucus, our plasma cells having produced antibodies that are going to be in the mucus. They're going to help fight the infection. You know, hear me? Anyone who's taking proton pump inhibitors regularly, better get off of them. Listen to me when I tell you this. Anybody you know who's taking proton pump inhibitors regularly for acid reflux, you tell them, Professor P said, change your eating habits. Start eating more papaya. Get off the proton pump inhibitor because you're going to increase your risk for infection of Helicobacter bacteria, which will cause gastric erosions. How you like that? All because you're taking the, you know, my grandfather, he died of that, yeah? My grandfather used to like sucking on Rolaids and Tums. And I gotta be honest with you now, he used to eat almost everything and anything. But he never went to the doctor. Sometimes you have no other choice but to take these medicines. Understand, guys? Understand the risks that are involved. That's what's important. And that's what's your job as healthcare workers. You understand? You have to be aware of this because you have to make sure your patients are made aware. So it's your job to be aware. Yes?
Do you know how we love pepper? Different types of pepper. Is that kind of like a negative?
I mean, the only thing that I know two physiological responses that pepper have. Right? Similar to cinnamon and some of these other types of, spices. One, they'll blow your taste buds out. So you like, the moment you put this stuff on there, it blows your taste buds. You can't taste anything for at least another 7 to 10 days or something like that. While they replace, the taste buds get replaced. Separately, you get this massive sympathetic response where you start sweating, right? Which, hey, may not be a bad thing, right? That little stimulation, like you're actually exercising, right? We do that. We do that when we do a stress test. We give a substance that creates a very similar pharmacological effect in the heart and will cause a sympathetic response, a massive sympathetic response to occur. If we're afraid that that person can't exercise on the treadmill, then we'll chemically induce them into exercise. At least the heart. You understand? And then measure the heart and lungs capacity together. Huh? So that's like, again, medicine. Diagnostic stuff. You get me? We'll talk about other stuff too, which is really cool. You put a person in a box and this is the only time you ever administer carbon monoxide, guys. You hear me? Now, you put this person in a box, you administer them a percentage, a small amount of carbon monoxide that you can read. And they breathe it in the box. And then you do is as soon as they're done breathing in the box, you take them out the box and you pull a blood sample and you measure the carbon monoxide in the blood. Now, why would I give them carbon monoxide? Well, because if I give them a certain amount that I know is measured, a metered amount, and then I pull those gases, I should see a proportionate amount of it into the bloodstream because it has this high affinity for hemoglobin, higher than oxygen, and binds to it immediately. So you only need a small amount. It's poisonous, it's colorless, odorless. But you can use it as a diagnostic tool to understand the thickness of the respiratory membrane. Did everybody hear me? Because if the respiratory membrane is too thick, then whatever I give and whatever gets into the bloodstream is going to be less. You understand? So it's a direct indicator. All I gotta do is just pull the sample. Oh, he's got a problem with his lungs. See how easy that is? We're not there yet. We're not at respiratory membrane yet. But you guys already understand that the lungs are in series with the left and right heart. Yes? That's the first step. All right. So, but today's discussion isn't about so much the B cell. It's about any cell. Did everybody hear me? It's about all cells. Did everybody hear me? It's about any and all cells. Because every cell, separate of making protein that goes, separate of making RNA. So remember, we make the DNA here. It goes to RNA. RNA leaves. You make protein. Send it to the Golgi. It gets modified. And then the Golgi decides whether or not it goes on the membrane or goes out the side of the cell through a vesicle. Did everybody hear me? Through exocytosis. Everybody hear me? Now, what am I missing in this story? I said, Professor P, man, I already know this. Look at him. He's young. He's asleep. I'm boring him. He already knows this stuff, right? Because I'm in chapter 3. And you would think, well, what are we doing in chapter 3 when we should be doing what? Immune. So we'll go back to chapter 3 and 4. Huh. What am I missing here? I'm talking about protein. I got protein for the membrane. I got protein outside the cell. What am I missing? Where's my protein no, I got the membrane bound one. There's membrane bound modified protein there. Here's membrane, here's release. Let me write that. Modified protein. All right? So that's my Golgi. That's my rough ER. What am I missing? Free-floating ribosomes, guys. Free-floating ribosomes. What do I need free-floating ribosomes for? Oh, because remember, there's some RNA that doesn't go that route. Doesn't go the route of what? The route of the rough ER. It looks like Professor P's making a connection here. So you got free-floating ribosomes, and what's their job? To make what? Protein. It's the job is to make protein. If it's on the ER, it's because it's making protein there. If it's not on the ER, guess what? It's still making protein. It's making it in the cytoplasm. Did everybody hear me? So we got cytoplasmic protein being made here. So now we got systolic. I don't want to use systolic. Cytoplasmic proteins. Well, man, that list is forever, isn't it? Give me examples of cytoplasmic proteins. Give me an example of a structural cytoplasmic protein. Ho. Good. Centriole's a good one. Okay, what else? They classify it under what? Under intermediate tubules, huh? What else we got? Microfilaments and then microtubules. Everyone agree? And under microfilaments, you got what? Actin and myosin. Oh! Everyone agree? Oh, that's chapter 3. That's chapter 3. That's chapter 4. That's chapter 5. You're talking about muscle. You're talking about bone. You're talking about extracellular versus intracellular. All right, so let's talk about this. The intracellular, the cytoplasmic protein. Well, every cell in the human body has its job to do, which is make protein. But at the same token, it can't always be making protein that it doesn't sample. So what is it sampling it for? It's sampling it to the immune system. So it's processing it to sample it, to see how well it's been engineered, and then present it to the immune system. Did everybody hear me? Every cell in the human body has this process. So when you make cytoplasmic protein, any and all of it can get ubiquinated. And ubiquination is just, let's say this is protein inside the cytoplasm. You're putting a whole bunch of UB to the nth. UB to the nth power, guys. You see that? UB is ubiquitin. So when I put multiple ubiquitins on, yeah? When I put multiple ubiquitins on any protein that's inside the cytoplasm of the cell, I target it for destruction. Did everybody hear me? How do I break it down? Oh, man. Check it out. Everybody know what a dicer is? What's a dicer and slicer? You guys have seen them before, right? Ronco, right? Ronco comes out. You remember Ronco? See, I'm dating myself now, right? Because Ronco used to be this company that would come on with the 2-minute and 2-second advertisement for all kinds of stuff that you didn't think you need, and then when you saw it, you're like, oh my God, I could use that, right? So you remember the one that's got the blades? They're like a zigzag, or they set them up upside down, and it had a little container, and you just put it on, and you press it, and it turns, and it slices and then turns, and then you press it down, it slices and turns. So it'll dice for you. Then you take that one off, and you lock it, and it'll slice for you too. So a slicer and dicer. There it is, Dan. A slicer and dicer. Well, we got these slicer and dicers inside the cytoplasm of our cells. And their job is, the moment a protein gets ubiquinated, they chop it up. Like a good chef ought to. Give me that protein, man. Let me chop it up. Let's cook it. Chop it up sometimes, right? Sometimes you cut it up. So we're going to cut it up. And what comes out the other end is what? Fragments. Everyone agree? Fragments. Those fragments are in the cytoplasm of the cell. They're self-protein fragments. This is how our immune system recognizes our cells as self from non-self. Do you understand, guys? And ultimately, those cell fragments are going to get uploaded onto an MHC class 1 marker in vesicles and put onto the membrane. So that MHC class 1 marker is going to come on, and it's going to take that self fragment, and I'm going to draw it. Ready? I'm going to draw MHC for what it really is. That's what it really is. And then if that's the protein, the MHC class 1 is like this little ball protein, and then this like these 3 connected on one. So you got this one protein that's got 1, 2, 3, and then you got this other protein that sits in there. And then the cell fragment, let's just draw it as a star. There's your cell fragment. Everybody see, guys, how I drew this and said, oh, there's that A, self-antigen with epitope. Everybody see that? Self-antigen with epitope.
That's what the star is?
That's what the star is. It's the epitope. The whole strip is the self-antigen, but the epitope is what's going to be recognized. You understand? The epitope is what's being presented. And all cells can do this. All cells. That includes B cells. That includes T cells. Now, so does everyone agree? Yeah, hey, this is a great mechanism, right? Great. Phenomenal mechanism. But is this just the cell all by itself? Is it all by itself in the environment? No, what does it have to contend with? What? All kinds of stuff, right? Viruses, prions. Remember we were talking about all that stuff the other day? All right, so let's talk about viruses. Ready? Why viruses, Professor Pete? Oh, because viruses, whether they're DNA or RNA viruses, guess what? They look like spiders. They come down and they attach and they inject their DNA or RNA into the cytoplasm. So wait, so does that mean then if my DNA or RNA that's viral in origin gets incorporated, or if the DNA gets incorporated, or if the RNA goes off to ribosomes, will that make cytoplasmic protein? Will that cytoplasmic protein be ubiquitinated? Will it be presented on the membrane of all cells via some MHC class 1 marker? See that method to my madness, guys? You see that method to my madness, guys? So the MHC class 1 markers are designed for what? For self-antigen and for viral antigen with epitope, huh? Everybody see that? Self-antigen and viral antigen. Woo! Why? Because they both made the cytoplasm of the cell. And we're what? Our DNA is what? 7% viral in origin. Now you see why the immune system can get screwed up? You see why the immune system can get screwed up? That's one way. One way. We got 5 different ways. 5 different ways. What do you mean, Professor Pete? You got viruses to contend with, don't you? You got bacteria to contend with, don't you? Then you got the other guys, right? The ones that come out the bottom end, right? Like the pinworms, like I told you. The only way to diagnose those is you get the baby and at night you put the piece of tape on the baby's bum bum in the middle of the night, in the morning. The little worms will come out to get oxygen. The baby worms will come out and they'll stick to the tape. And that's how you diagnose pinworms in an infant. Tapeworms can be as large as the intestine. So, and I can tell you that worms are difficult to treat and get rid of. All right, this is what I'm dealing with now with this dog. All right, with my dog, he's got some kind of worm, and he's already been on 3 different medicines for it. I'm hoping he's going to be cleared, but I doubt it. Doesn't look like it. So he may have to wind up taking another course of it. Hopefully not, because it's a real pain in the rear. But if it's got to be done, it's got to be done. Trying to feed him right. Trying to teach. I'm staring at his poop regularly. Trying to examine what's going on with him. So, yeah, man, this happens when you. It's all right. So self-antigen, viral antigen, guys. Cytoplasmic protein, MHC class 1. You understand, guys? You understand that? Yes.
So will there be bacterial antigens as well?
There will. Absolutely. Of course, those enter via a different mechanism. That's what we're going to talk about now. I'm going to erase this. Video's on, so it'll definitely be online. Right? I'm disciplining myself to go home and do it. Right? And load it up. So I'm going to erase this now. All right. Now, that's all cells. So all cells have this ability. Only 2 cells in the human body have this other setting. So only B cells and monocyte macrophages Okay, monocyte macrophage. Only those two types of cells will use the MHC class 1. So why is this and how is this? Okay, well keep in mind, let's talk about the macrophage and let's talk about bacteria. So if I have a bacteria, there's my bacteria. And my body, right, luckily I have antibodies. Now, with or without antibodies, a macrophage can engulf this bacteria. Now, I'm going to draw this bacteria much larger. Okay, guys? So, because I need to draw stuff on the surface. So there's really two types of bacteria. Well, there's three major types of bacteria that exist in the world that cause disease in humans. There are those that are called gram-negative because of the way they stand, those that are gram-positive, and those that are atypical. Now, there are other ways of classifying based on shape. And you'll learn this in micro. So you have staph and strep, right? And you have cocci and bacilli, right? And what really matters here is this. I'm giving you microbiome in a nutshell, you guys. And then some people say, well, how come you're not teaching microbiome? Because I learned more in your class than this one. And it's like, I don't know, get me started. All right. So gram-negative. Gram-negative is important because of why? Because of this thing called the LPS. And gram-positive is important because of this thing called teichoic acid. And in atypicals, there's one in particular called TB that has one called mycolic acid. You see what's going on here? And then this is called actually lipopolysaccharide. LPS. Everybody see that? Now watch. These are bacterial antigens. With known epitopes. Right? There's gram-positive, there's other stuff. It's not just this, but there's other stuff. But teichoic acid plays a huge role. Lipopolysaccharide from gram-negative plays a huge role. Mycolic acid from TB plays a huge role in stimulating immune system responses. You understand? I already told you the case of the TB, right? My friend got coughed on, right, on the bus in Dominica, right? Not Republican Dominican, right? Or Dominican Republic. Dominica is a small little island. This is where they have a medical school there. And they're predominantly Brits, right? They're Brits. You get some, some of the other islands are settled by Netherlands, but they're predominantly Brits. And you get coughed on, and the TB goes into the lung. The macrophage tries to destroy it by engulfing it. And it realizes it can't. It calls upon others, and they wall it off, and it creates what we call a Gone complex. You take a chest X-ray, you'll see calcifications. You'll never do surgery on that Gone complex. You'll never touch it, because if that TB gets released into the bloodstream, you get miliary TB. You're going to get DIC. DIC will lead to your death. You understand that? It's called disseminated intravascular coagulation. All right? The dick that does not put a smile on your face. Okay. All right, I'm not judging nobody. Okay, it's all good. But this is the one that does the complete opposite. Okay, that's DIC. You don't want none of that. You don't want none of this.
So how do they treat it?
They don't. You're lucky to be alive. My aunt got it. She's lucky to be alive. You get sepsis, it leads to DIC. Be careful.
But I mean, like the calcification, because you say.
Oh, the calcifications, that's just because the macrophages are constantly trying to secrete, and they're fusing and secreting and create these huger cells.
So they leave it alone?
Okay. The macrophages are like, oh yeah, we can't handle this, yo. Yeah, let's just wall it off, bet. And that's what they do, they wall it off. And then you'll see it when you go to take. So when you go to do you can do the titer. Or you can do the skin test, the TB skin test. It comes back positive. You take the chest X-ray, sure enough, you'll see it. Huge calcification in the lung, guaranteed. Guaranteed. You never touch it. Touch
Yeah.
it.
So if it breaks
Remove
off,
it, operation.
Yeah, try to do that. People wind up dying. Hey, don't touch it. Leave it alone.
what if it breaks off though?
Hey, it doesn't rarely does that because the macrophages are really good at walling it up, but you don't ever want to touch it. Can it pop and burst on its own? Yeah. Can it cause an empyema? Yes. Can it cause lung? Yes. Because if it's close enough and it gets walled off and it affects the surface of the lung and it pierces that surface of the lung and it changes the pressure inside the lung will collapse. It all depends on where it seeds. See? It's dangerous. Stuff is dangerous. And you're around it all the time. You just don't know it. You guys don't know it. Yeah, remember what they call Miami? The capital of Latin America. Oh, y'all know that? The capital of Latin America. That's right. People coming from all over the Caribbean. And people in the Caribbean, man, they got this stuff. There's no joke.
But if you have a vaccine for it, you're okay, no?
If you've been vaccinated, your titers are high enough, yes. Did everybody hear me? If you've been vaccinated and your titers are high enough, what does that mean? What are titers? What is clinically, what does a titer mean? I know I'm going off topic for a moment, but what is a titer? Clinically, what is a titer? The concentration of antibodies in the plasma. You see? So if I vaccinate you, then I should turn around. And we'll talk about vaccination. I should turn around and at some point I should see some normal response, an elevated titer in antibodies in your plasma. And they should be long lasting. Because the antibodies, even though the plasma cells don't stay around forever, some do, some linger, but not, the majority don't. They respond and they stop. But some do stay, and with the proteins that they generate are long-lasting proteins. These antibodies, they wind up being found on the mucus and in the plasma, waiting for this bacteria to show up the second time. And why is this important? Well, again, if I draw the bacteria now, I draw it nice and big. You ever see I drew it nice and big now? If I draw it, that bacteria has no nucleus. Now we're microbiome. It's got no nucleus. It's got ribosomes, but ribosomes, remember, are nothing more than enzymatic proteins. That's all they are. It's got RNA polymerase. It's got DNA polymerase, which means it's got DNA. It's got RNA. Huh? Yeah. But it's got no mitochondria. It actually acts like mitochondria. Because mitochondria are like it. Now, but we're not talking about none of that, because that's microbiome. I should be teaching microbiome, you see? Now let's imagine that there's a protein here that has that antigen, that epitope. So there's a protein on the membrane and it has an epitope that it recognizes. And now imagine that you've been exposed to this guy before. You make this antibody. There, you see that? Now, you could have different antigens. Now watch me. Circle. So I got star, circle, square, and triangle. And I could have an antibody recognizing each and every one of them. Everybody see that? Now, when that happens, then, remember we talked about this? The FC region, the constant fragment region of an antibody. Remember, I'm drawing it real simple because it should look something more complicated. The antibody should look like this, with light chains and heavy chains. Everybody agree? And it's disulfide bonds in between. When these guys have the ability to recognize antigens or epitopes, antigens that have epitopes on the membrane of the plasma of the bacteria, then what they can do is aid the macrophage, the monocyte, via receptor-mediated endocytosis. Because watch. So let's put, all right, let's put the Jewish star of David. Right? Let's put my Jewish star. Now, if we have that, and then we have the heavy chains in. Over here, there's the FC receptor. And we say, well, the FC receptor is different. The FC receptor on the macrophage monocyte are different from those on mast cells. Yes? But they're still FC receptors nonetheless. So there's subtypes of FC receptors. And when you do this, and this is happening, these are anchored to this, and this gets anchored to that. Well, this is called opsonization. Pretty sure I spelled that right. All right, opsonization. So when the antibodies that a B cell makes coats the bacteria, and it's called opsonization. Everybody hear me? And when you have opsonization, then that will increase the macrophage's ability to phagocytose via receptor-mediated endocytosis. Everybody got me? Any questions so far? So receptor-mediated endocytosis is saying, oh, so I'm bringing the bacteria in, and the antibodies are surrounding it. And now it's in this phagosome. Everybody hear me? And now I got what? Oh, well, I got lysosomes. And I got peroxisomes. And I can merge them. Everybody see that? And dump the products into the vesicle. So now I make this harsh environment for the breakdown and destruction of the bacteria. Did everybody hear me? Did everybody hear me? Now, what did I tell you though? Yo, I start breaking that bacteria down, and what am I going to release if it's gram-negative? Lipopolysaccharide. That's toxic. This is gonna cause an immune response. So if I start breaking down that bacteria outside, which can happen, it can start being targeted already outside the cell, and I get this release of this stuff, any one of these in the bloodstream, guys, I'm going down a path that's not good. You already follow? It's called sepsis. All right.